Hi, before I begin, and I want 5 seconds before you start your timer, I wish I could use VR in this. So I hope I can amuse you as a VR audience, and perhaps you will find a way to look at what I'm looking at through the dynamic tools which you use. So I'm privileged to work, I'm a lighting designer. I'm privileged to work with a group of low vision scientists at the University of Minnesota and at the University of Utah, including cognitive science, low vision expertise, computational vision, and so on. Whoop, this click. So why is predicting visibility important? And our goal is to create tools, or we've created tools, which an architect hopefully will eventually use during the model phase of their design process to include the world of low vision. And why? In geographic Europe, there are about 26 million people with low vision. Definitions are in the above. And currently, the low vision community has visual ability, but we are not designing for it. We use what we think are tricks, and I think I'll show you how some of these tricks don't work. We're not actually evaluating our spaces for low vision individuals. So what is a visual hazard? Unseen edges within our path or our route, the potential to cause harm, right? Steps, ramps, protruding corners, even the edge of a subway. And so here's an example. Currently, lighting designers use illumination as their metric. So this box has got a 80% reflector on one side and 20% otherwise. Both of the images are rendered under 300 lux. And there's a visible edge, imagine it's a staircase. I move the luminaire 60 centimeters, and suddenly that reflective distance difference has completely disappeared. So design by luminance is what we need to do, not design by illumination. Luminance is how we see. So just a little precursor. We see by acuity and contrast, there are two main factors, right? And those end up in a contrast sensitivity curve, which I can't go into today because my 9 minutes are remaining. But basically, we worked on the work of Eli Pelly. We built filters that would match various visual acuities by studying people. Can you see that step from 20 feet away if you have this particular low vision? And we modified the constants within this variable. So we can now have a tool that filters an image in a way that obscures items which that person in that acuity should not be able to see and leaves visible the remaining part of the scene. So this is fundamental to the tool I'm going to show you. So how it works, so the visibility prediction tool is that we start, in this case, with a radiance rendering, right? It's a photometrically accurate rendering of a scene. And from this, we do two things. Number one, we data mine back to the source geometry and find out what is the ground truth edges within the scene. What are the potential hazards? Secondly, we take the same image and we use our filter to blur that image, right, to a particular acuity. In this case, I've just labeled it severe low vision. From that blurred image, we then look for the luminance steps within it and find these luminance patterns, right? And I think the next might be obvious. We take the ground truth and compare them to where there is no luminance pattern and predict that to be not visible. So in the image, red lines, not visible, green lines, visible, no ambiguity. So let's run through a couple of examples. This is the Washington subway station, which I modeled. There's believe it or not, a bench in the middle of this. Under severe low vision, that bench is predicted not visible. By the way, the orange line simply, we block out everything below 1 candela per meter squared. It's a different visual condition. So let's change the bench to white, see what happens. Mild low vision, moderate low vision, legal blind threshold, severe low vision, profound low vision, I'm not sure, but at least I can see the leading edge isn't going to be visible. One more change, let's add a bit of lighting to the original darker bench. Severe low vision, the front edges of the bench are visible. Severe profound low vision, that light pole is suddenly not visible, right? So, it's a changing dynamic. So what we're trying to provide an architect with is not a prescriptive solution. You have to use a 6-inch yellow line. We're trying to provide work within your visual vocabulary to get a good score. Score? Well, we've come up with a hazard visibility score. Within the whole field, we suggest a region of interest, a potential hazard, in this case the bench, and we run an analysis on it. A score of 1 means it's highly visible, it's going to be seen at a particular acuity, and a score of 0 means totally gone, not visible. In this case, you'll see 0.8 is maybe where we should have a standard. Below that, it's not very good. Let's go now use a white bench and lighting, and for all the way down to severe vision, we've got a passable visual score. This is a metric. You can write code if you have a metric. There's something to comply with. Let's look at the edge that you might fall off. In both cases, severe and profound, I think we predict it's reasonably visible. So here's a case study. This environment hires people with low vision. This happened to be the result of a design that I was given the model of. They changed the width of the step, but everything else was the same. I have blurred the central image of the photograph using our filter, which you can do if we have the view angle information in the photograph. And I filtered our model. Okay, so I deconstructed it. Let's see how we score here. Mild low vision, you're not going to like it. Wait a minute, this gets really interesting. It's invisible to profound low vision. You don't know there's an aperture there, let alone a precipice to fall down. Make some changes. Let's change the color of the floor. You'd expect to see the leading edge of the step and the end edge of the step to be visible because there's a contrast edge, right? Let's add an edge down the staircase. More visibility, still not a particularly good score. The final result was putting the white stripe on it, which they did in the model. All the way down to severe low vision should be able to see the hazards in front of them. Profound low vision is pretty bad. Got to work on this, except the leading edge alone might be what we need to work on, so at least someone with profound low vision knows there's something coming up. So here's a daylight study because we want some daylighting here. Same box, I put the skylight above it. Here we go. This is at 11 o'clock. At 11:30, that edge is completely invisible. Remember, 20% reflection on top, 80% reflection on the side. Keep going. Bam, we got it, right? So only during the afternoon with this staircase, potential staircase, be safe. So what this suggests to me is an annual atrium daylight hazard visibility study. Find the times of the day when the steps are not visible. I found this on the VELUX website as some atrium model that we're working with. Maybe times of the day you change the contrast in different places so the whole staircase continues to be visible and we're not limiting access to only those of us who have perfect vision. So our basic tool set, Radiance image, filter it to a variety of acuities, and get an end visibility result. There are other tools for diagnostics that we have that we're not looking at today. So validation is always an interesting thing. My science colleagues have been running and continue right now to be running both persons with full vision and wearing blur goggles and individuals with low vision, and having a look to see, does the hazard visibility score match increasing visibility? They have told me the hazard visibility score predicts human performance. So we actually have validated results that these tools are useful. There's one outlier in this, but again, there's not time to look at it. They reverse step up and step down. Limitations. This is view-dependent VR, people. Right? And that means a computation for every view angle and reflections off the floor become important. It requires lighting and material specifications, which might change a little bit where this tool might be used in the architect's process. High luminance areas can mask nearby low luminance areas. Well, that's pretty common to most vision, right? You can't see around the glare source. And strident high contrast material patterns can result in incorrect visibility analyses. I show you some of the types of patterns that have confused our system. And we're continuing to refine it. This is available or will be available through Ladybug. We invite developers who have interest. The code is open source. It's on GitHub. And Greg Ward, bless him, who you'll hear from him later, has written a specific tool in Radiance that extracts all the information we need while it's making the image instead of the clumsy pipeline that we are currently using. So he's optimistic, so I'm optimistic. So the DeVAS tools enable the designer to analyze and improve visibility of hazards, potentially within the design palette of the project. That's the key to success with architects, to aid in the generation of architectural spaces that are accessible to those with vision impairment who can make use of their vision for mobility. So standards could potentially be structured for luminance studies, such as these from DeVAS, where compliance is sought to a visibility metric standard. I presented this to the American Disability Act Access Committee, to the IES in the United States. I'm interested in talking to the well building. It seems to me a well building should be more than what you breathe or whether you have a view, but how about maybe you're not going to fall down the staircase as well. So with this, I thank you and look forward to some questions in a while. Cheers.